Who makes more money, the architect or the mason, the doctor or the lab technician, the factory owner or the laborer, the CEO or the receptionist? The reason the former profession always earns more than the later one in the earlier examples is that the architect, the doctor, the owner, and the CEO spend most of their time and energy in knowledge-based cognitive activities, while the mason, lab technician, laborer, and receptionist are compelled to focus all their effort on skill-based cognitive activities. So my question is simple and direct. To which category would you rather belong? Of course, it's a no-brainer. We all want to be paid more and have higher status. But we might not be aware that that is dependent on the way we use our cognitive capacity. If we use it just to do the job and operate the machine or follow the instructions, that's what I've been calling the skill base, which is related to the skill brain quadrant in my 4 brain learning approach. However, if we are able to use our cognition to interpret, analyze, structure, systemize, decide based on the results found by those engaged in the skill brain quadrant, then that's what I've been calling the knowledge base or the skill knowledge brain quadrant. And this is where the money and status power really lies. In the context of this chapter, the skills aspect of statistics are all the steps from 1 to 9. That is from writing the proper research question, to collecting data, to organizing them and processing them, to finally get the report containing the results. The knowledge aspect of statistics, step 0 or observation, and step 10, interpretation. In the lingo that we used earlier, it's where the money is. Of course, the good old professor will not tell you this because either he doesn't know it himself or he doesn't want you to be rich. Moreover, as we will learn in the later section, steps 1 to 9 can now be outsourced to artificial intelligence. Of course, it's not that quick and simple, and there will always be a lot of human cognition required. So it's a kind of autopilot state. But we'll discuss that later on. For now, in this section, I want you to understand that if you can master step 0 and step 10, then the other 9 steps are not as hard as it was during your professor's days. In his days, only the smartest of the smart ones could do and specialize in step 0 of observation and step 10 of interpretation full time. Now, anybody can. I believe that more people should be able to do because there are so many things to discover and so many things to interpret. So let us begin this lesson in the observation and interpretation of statistics. Many of the terms that we are going to discuss here, you have already encountered them in the earlier sections. So I will assume that there is much familiarity with regards to them in you, the reader. I will be referring to the tables in the diagram below. So like in the earlier sections, if you are lost, you too can refer to them. To make this exposition interesting, I will start from the example, which is actually the observation, and then I'll move to the statistical output and what it means, or what we can interpret from it. I'll repeat this pattern throughout this section. Let's say you are going on a house hunting spree. The agent shows you around. After a few days of visits, you would have been shown around dozens of houses. Each of them will have different prices. You now have a problem. You like a particular house, but you want to know if the price is right. So you need a comparison. Comparison to what? It's where the mean comes. It's the typical value or center point of the data set here, which is a dozen house prices. So let's say that you calculated the mean for the various houses that you went to be $350,000, and the house that you liked cost $370,000. This means that your choice is above the average market rate. Now you know that it's more expensive than the average house, but since you really like it, you can safely say that it's worth $20,000 more than the average. In this way, you can interpret simple mean, feel good about your decision. But if it was $450,000, that would have been $100,000 more than the market rate. The mean could have provided you the basis to question your choice seriously. Is that extra bathroom and view worth one more grand? In this way, you could interpret the mean as an objection to your earlier decision. That could have saved you lots of money and lots of future problems in the form of installment payments. In this way, a mean is much more than just a number, right? And this is how CEOs think, and that is why they are paid more. Our fear is always that we are made a fool of. When it comes to salary, it matters less what our income allows us to buy, but more how we stand among our peers. Am I poor or rich? Am I underpaid? We might ask our colleague how much they are paid, but that would only provide us with one reference point. We could ask two, but that would only be two reference points. So this is where the concept of median comes in. The middle value, or the exact middle value when all the data points are lined up from the smallest to the largest. Let's say we found out that the median income in my line of work is $55,000. This means that half the people earn more than this and half the people earn less than that. Then let's say that my own income is $65,000. So should I be happy or unhappy? Well, I earn more than half of the population who are engaged in my line of work. So I'm not underpaid, but there are more people who earn more than me, and it's okay. I don't have to go to my boss and resign for having been ripped off or exploited. It's amazing that some people can never find the size they are looking for their shoes. Have you ever wondered why? Well, it's because of the mode. It is the most frequent value or category in a data set. The shoe factory and the shoe shop produce and stock shoes of the size that are mostly sought after. That again depends on the most common shoe sizes people have. In this particular country, the mode of the shoe size is 9. That means that most of the people have a shoe size of 9. So obviously the factory will produce more shoes of 9 and the shops will stock more of them. However, if my own shoe size is 11 or 6, I'll have trouble finding the right size for me because it's not within the mode. As a principle, just taking the average score for a test can be deceiving. Is it that everybody scored that particular average, or is it that some outliers cause the high average or low average? So this is where standard deviation comes in. Is the average amount of variation or spread from the mean. As an example, let's say the average test score is 75 with an ST of 5. This means that the most students score between 70 and 80, that is 75 plus minus 5. That's not bad. So the principal will conclude that this class is quite homogeneous. However, if the ST was 20 and the average was still 75, the principal will conclude that there are too many outliers. Some are exceptionally good and some are exceptionally bad. Nobody likes fluctuations, but they are a reality. It's better to be prepared for them than unprepared. That's where the range comes in. Is the total spread of data the difference between highest and lowest values? For example, minimum temperature was 10 degrees and the maximum was 30 degrees. So the range is 20 degrees. Most likely it was 10 degree in the morning and 30 degree in the afternoon. So that must be a very fluctuating place. You would need a jacket in the morning, and in the afternoon you'd need to stay in the cold AC. Alternatively, this range could represent temperatures at different times of the year, 10 degrees in the winter and 30 degrees in the summer. That would be a very nice place to stay, neither too hot nor too cold. You know what's the difference between height and wealth? Height is mostly uniformly distributed across the population. Most of the people have an average height, with some being very tall and some being very short. But is it the same for wealth? This is where Guinness comes in. It measures the asymmetry of the data distribution. According to economic research, there's a positive skew of plus 1.5 in wealth distribution. It means that the majority of the data or net worth of individuals is on the lower end, with a very few very high outliers pulling the mean to the right. That's quite obvious, right? Where the term 90% of the wealth is owned by 10% of the population. That's an example of positive skew. So far, you have observed and interpreted the various phenomena and outputs of descriptive statistics. Now let's repeat this process for inferential statistics output. Remember, this knowledge-based cognition or highly evolved knowledge brain quadrant is what's going to make you rich. So be very mindful while you read this section. Let's say there's a pharmaceutical company that comes up with a new drug. Should the government allow it in the market? Yes, but before that, medicine must be proven to actually work. You don't want to be selling a placebo effect. This is where inferential statistics comes in. There is a control group that is provided sugar pill, and the experimental group that is provided with the actual drug. Mind you, both of the groups suffer from the disease that this drug is supposed to cure. Now the various 10 steps that we discussed earlier are completed, and the results comes as a p-value. Its range is usually from 0 to 1, and it's a probability. Low value of p less than 0.05 means that the result is statistically significant or that it is not a random occurrence. A value which is p greater or equal to 0.05 means that the result is not statistically significant and that it's most likely a fluke or random. So in this particular example, report came with a p-value of 0.003 for that drug. Since 0.003 is less than 0.05, we reject the null hypothesis and conclude that the drug has a real effect. It means that the drug is not a placebo and that it really cures the disease that it's claimed to cure. So yes, the government can now allow it to go to market because it's a real deal, as proven by the inferential statistics 10-step process and its final report. Let's get into the seat of a politician who is running for office. He has segmented his voters list into various categories. He wants to know whether there is a relationship between gender and political party preferences. Do males prefer a certain party as opposed to females? Alternatively, is a certain party more appealing to a particular gender? Here we are not trying to understand the theory or the why there would be such a relationship. We just want to know, is there a relationship, yes or no? So this is a purely category to category type of data set relationship. In order to answer this question, our team will do inferential statistics and go through the 10 steps that we outlined earlier. It will provide us a report with the chi-square, which is ranges from 0 to infinity and is always positive. But what it does is it gives the measures of strength of association between two categorical variables. The higher the value, the stronger the evidence of the relationship. In this particular study that our team conducted, it was found that the chi-square value was very high in the 1000 plus, which suggested that there is a relationship between gender and political party preference, and it's not due to random chance. Now that as a running candidate, I know this, I can target my policy promises, be very gender specific, and trying to get as much votes from both genders. And if I realize that my party's policies are very unpopular for a particular gender but popular for the other, then I will drop the idea of trying to woo the gender that doesn't basically like me and focus fully on the one that likes me, hoping for the best. We have slightly touched it earlier on, but there is always this question is that does the number of study hours affect the exam scores? We all had classmates who claimed to never study and still got high marks. We saw them hang out, fool around when we were studying, but they always aced the class. They said that it's not the amount of time you put in your studies, but it's just pure luck or how smart you are. Then our parents and teachers have the opposite theory that no, it's the number of hours that you put in that will improve your exam scores. Who's right? Our lazy but intelligent friend, or our boring but hardworking influencers? So to put this debate at rest, you can conduct inferential statistics study using the 10 steps. In fact, it has been done so many times across the world, so I'm just pulling data from old studies. After the 10th test, the report will give us the Pearson's R, or the correlation coefficient. It would range from -1 to +1. Then the positive value of R greater than 0 means that the variables move in the same direction, and a negative one means the variables move in the opposite directions. Remember, we are here talking about both the dependent and the independent variable being of numerical category types, and that's why we use the Pearson's R as an output to measure significance or correlation. In this particular example, we have R is equal to 0.85. So it's positive and almost near to 1. This means that there is a strong positive correlation between the number of study hours and the exam scores. Basically, our smart friend was lying through his teeth, and our parents were right. As the study hour increases, exam score tends to increase. Yes, of course, there are some exceptions, as you can see with the 15% less for R being equal to 1. But for the majority of the students, in most of the cases, the harder you study, the more scores you'll get. It's settled. Go back to your studies. Now let's say that we want to introduce a new teaching method in our school or college. We claim that the mean score that will result from it will be higher than the old teaching method. Well, it's not enough that you claim it, it has to be proven. So it's pretty much like the drug test earlier on. But first we need to find out whether there is something potential in the new method and it's not just noise. We want to know whether there is a relationship between the teaching methods and means of the scores. Again, we put this hypothesis in under the 10 steps of statistics by designing the proper experimental settings. We could assign 3 classes where the new teaching method will be taught and 3 others where the old method will be taught, and we would do various statistical tests, among which test mentioned here. Its range is from -infinity to +infinity and is measured in standards of errors. This statistical output or measure is used. The dependent variable is a categorical one, and the independent variable is numerical one. That is, the old method, new method is used, yes or no, and the mean of the scores respectively. A positive value of t means that mean of group 1 is greater than the mean of group 2, and a negative value means that the mean of group 1 is less than the mean of group 2. So in our example, t value came out as 3.2, where the group 1 was the new teaching method and the group 2 was the old method being used, the various classes. Because it's a positive, means that there is a strong correlation between an increase in the mean scores of the group and the new teaching method. Basically, it's saying the new way of teaching is effective, so go ahead, green light, roll it out across all the various classes in the school or college. We all know that exercise is good for health, but how much exercise is actually good for how much health? That test be done with inferential statistics again. We would put, let's say, 100 people with high blood pressure in an exercise regime of various hours, and we will be measuring the blood pressure after the exercise. This will provide the data set. After running the 10 steps of statistics, the report will give us the statistical output called regression coefficient or beta. The range is the unit of outcome variable or unit of predictor variable. What it does is quantifies the impact or magnitude of the predictor on the outcome, and the plus or minus sign indicates the direction of the impact. So in this hypothetical example, we found out that beta is 0.75. This means that for every 1 unit increase in exercise, that could be 1 hour or 10 minutes, the blood pressure decreases by 0.75 units. Isn't that encouraging? Now, the doctor can convince the patient even more easily. It's not just a good advice, it's a tested, proven advice now. And that's what statistics, especially information statistics, does. Let's say you want to place an ad for a new product or for your own house that you want to sell on a web portal. Your question of definitely is, my house sell if I provide exclusive right to that particular web portal, sell my house. What you would like to know is, actually potential buyers come to that web portal? The marketing guy for that website will definitely say that it's a hot cake. But after studying this chapter, you should ask for the predicted value or Y of that website. It means the model's best calculated estimate for the outcome given a set of input data, and the unit is the same as the outcome variable, e.g. probability. So the marketing guy of that web portal would say that they conducted a statistical inferential study on the click rates over 1,000 clicks, and their predictive model has concluded that there's a 92% probability of users clicking the ad of your house. Again, that data is provided by a predictive engine, most likely powered by Python or artificial intelligence. They use complicated formulas based on dozens, if not thousands of data sets. Human mind couldn't do those calculations, so only computers can do them nowadays. So as a bonus, the marketing guy asked the predictive model to predict at what rate the house you bought earlier of the market value of $350,000 sell, and the model predicted your house would sell for $410,000. Isn't that genius? Of course, you're gonna give exclusive rights to that web portal to sell your house, isn't it? So by end of this section, sure that you feel empowered, enlightened, elated, have been elevated level of knowledge-based cognition or a fully developed knowledge brain quadrant. Welcome to the world of architects, doctors, owners, and CEOs.